Good afternoon, everyone, and welcome to today's colloquium. It's my pleasure to introduce Professor Gil Refael. Gil did his undergrad at Tel Aviv and his PhD from Harvard, working on disordered systems, looking at, and later he's been working a lot on quantum information, entanglement entropy related ideas. He was among the first people to kind of come up with this idea of that using one-dimensional superconductors to realize Majorana modes, which was a great interest in the quantum information community. And he's also been very influential in kind of, bringing up this idea that one can use driven systems using light driving, this thing that he'll talk about today, using Floquet systems to realize new phases of condensed matter. So without further ado, let me welcome Gil. And regarding questions, do you want me to? Yeah. So if people have questions during the talk, I mean, Gil said it's fine to just feel free to raise your hand and just ask a question during the talk. All right. Thanks.
Thanks so much. Hi, thanks. It's really a pleasure to be here. So I was very happy to get the invitation from Arun after not seeing him for several years. And I have to say, Arun and I were office mates at some point. We were postdocs. Not only that, Arun got his first American license, I think, on my car. Is that right? I'm remembering this right? So I trusted him very deeply, even back then. So again, thanks for the invitation. It's a pleasure to be here. Like Arun said, please ask me questions during the talk. I have some idea that maybe this is a little pedagogic. So if you start getting lost, or if you're just curious about something, ask me. I'll repeat the question just for the Zoom audience. Right, so my talk today is about topological principles applied to light matter interacting systems. So over the last 15 years, 20 years, there's been an explosion of developments in topological quantum physics. It made us reassess materials, reassess what materials can do and how they can behave. And maybe you heard so many talks about topological physics over the last few years that you started to think that condensed matter theorists are starting to do more string theory than condensed matter, whereas actually the situation is the opposite. I think string theorists are doing more condensed matter now. But that said, I wanted to go back to the origins of topological band structure, talk a little bit about the basics of churn bands, etc., and then show you how the same principle of topological physics can be applied to could be applied both to use light to control topological properties of material, produce new devices like far infrared detection using topological material. That's something I'll mention but not talk about. Think about new types of bosonic excitations of material, like new kinds of polaritons. And finally, new paradigms for amplification of light based on this topological physics. So those are kind of the topics that I'll touch upon. And for me, it's a bit of a review of my career from 12 years ago to today. So some old stuff, some new stuff. I hope that's okay. It's always nice to talk about old stuff, because then you don't need to prepare new slides. Oh, oops, I'm being recorded. I should not say these things. All right, so let's start. So first of all, what is topological? I'm sure you heard many talks about topological physics. I'm guessing that some speakers by now just assume that everybody knows everything about topological quantum physics. So I won't assume that, but press the fast forward button if you do know everything. So what is topological? So the idea of topological is that it's a quantity that is invariant on the shape, but just depends on a particular feature of global shapes, not on the location of walls, etc. Particularly the number of holes, the genus. So just to explain this, if you take a piece of paper, now you can wrap it into a cylinder, into a ring, and now you can do one of two things. And those two things would be topologically distinct. One thing that you can do is you can take the two sides of this ring and connect them to a point. And that will make you, that's how you would make a lollipop. That would give you a sphere topologically, no holes. Or you can take this side, wrap it in, and connect it to this other side, which will give you a bagel or a donut, depending on what you like better. And I think every time that people talk about topology, they show some picture like this or like that, depending on whether they like bagels or donuts better. But what is topological in physics? So in physics, there are many examples of topology, even before this explosion of quantum topological phases. So vortices were around forever. In weather, for instance, we know how to distinguish between a day with clear sunny skies and a light breeze moving in one direction and a hurricane. Unfortunately, we know how to distinguish. Now, if you want to go from here to here, you need to take the eye of the storm outside of the storm. So there's a topological stability. There's a hole in this pattern that makes the hurricane stable. And only if you take it away, you can get linear wind that will give you calm weather. And one thing that I wanted to emphasize, what is the topology over here? What would I like to say is topological over here? If you look at the velocity vector around this hole, it wraps around the circle, right? Whereas, of course, one directional breeze would have all those arrows pointing in the same direction. Vortices appear in superconductors. If you try to put a magnetic field through a superconductor, the magnetic field lines, the flux line, will form vortices and go inside the center of the vortices. Again, a very stable configuration for superconductivity. And I wanted to add that not just physicists and mathematicians think about topology, that there are other fields that care about topology. So for instance, archaeologists seem to care about topology. So check this out. So this is one vase from the Roman Empire era. It's a jug with one hole. And I think it costs, back when I checked, it was costing $12,000. And check this out. This is another jug with two holes in it, so a different genus. And clearly, it's much more expensive than this one because this one is priceless. I couldn't find a price for this one. And even beyond that, you know, wine enthusiasts also seem to care about topology. So there's, for instance, an example of a carafe with genus 0, genus 2, one hole and then another hole around, and genus 1. And I didn't check those prices because, yeah, I was too scared that it'll show in the history of my browser. I'll start getting advertisements for all sorts of weird carafes. And yeah, and you know that you know, personal body art is also quite informed about topology, but I'm not going to dwell on this. So back to physics. What is topological in physics? What is topological in condensed matter? We talked about vortices in superconductors, but that's very 20th century. We don't talk about these things anymore. What is topological in topological phases of matter? So the most important for me today is spin, the electronic spin. So electron spin is described, it's a spin, electron spin is described by a two-tuple vector. It's a spin half object. And we write a wave function for the spin half that's based on the direction onto which the spin points, right? Remember this, cosine theta over 2, sine theta over 2. We can argue for half an hour where to put the e to the I phi, you know, the azimuthal one. I recommend this one. This way, there's no singularity when theta equals 0. But we can argue about that. But this is the star of the show, the electron spin. Now, just like the velocity winds around the eye of a storm, the direction of the spin can wind. It can wind in space. That would be like a standard magnetic vortex. But it can also wind in momentum space. And it's the winding in momentum space that gives you topological physics. So let's see that. So let's work our way towards a one-dimensional topological phase. So a spin orbit coupled wire would be a wire that has electrons moving around, has a p squared over 2m, say, energy. But in addition, it would have spin-orbit coupling. So momentum times SZ. So this is like a momentum-dependent magnetic field. If the electron is moving to the right, P would be positive. The spin would want to be up. But if it's moving to the left, this would be negative. You would want a negative spin as well in order to take advantage of the spin-orbit coupling energy. Make sense? Now, there's no really such thing as a quantum wire. The fundamental building block of matter is atoms. And the most quantum of wires would be a chain of atoms. And in a chain of atoms, you can't really have pieces in the Hamiltonian that are proportional to the momentum itself. You need to think about periodic functions of the momentum to reflect the fact, right, that the electrons are moving on a periodic lattice, right? So the energy spectrum of the electrons will break down into bands. And the very lowest band would have an energy that's closest to, depending on cosine of the momentum, with the momentum ranging between 1 over the lattice constant to minus 1 over the lattice constant times h bar pi. This corresponds to the fact that the smallest wavelength that an electron can have corresponds to this momentum is twice the lattice constant, right? Yes? That's a great question. So in atomic systems, it will be the spin with the angular momentum, right? Russell-Sanders interaction, all those things that I should remember from quantum 2, like Hund rules, all that stuff, right? Now, so this is all good and well to determine the orbital physics inside an atom. Now, if you have low-dimensional systems, for instance, like two-dimensional heterostructures, those occur when you sandwich semiconductors with different doping, one on top of the other. And then somewhere in between, you can have a thin layer with a depletion layer where you have an electron gas, right? Now, when you do that, automatically you get an electric field perpendicular to the two-dimensional layer. And then if you have electrons that move in an electric field, then there's the relativistic correction that says that velocity cross electric field is effectively a magnetic field. This is a relativistic correction to the field equations. And you can think about it as if the charge density that gives rise to the electric field is moving relative to the electron. So there's a magnetic field associated with that. And that is something that the spin sees. And now this is the pedestrian way of understanding the spin-orbit coupling outside the atom. This is what I described as the Rashba interaction. But then you also start thinking, but wait a second. I mean, some of the electronic orbitals themselves, they have some kind of a rotation between atoms that will give additional spin-orbit coupling that's basically understood in the same way, but with more details. Yeah, I see a question from the Zoom audience. Oh yeah, sorry. And the answer, well, I promised I will repeat the question. I failed. The question was, spin-orbit coupling is something that happens inside the atoms typically. How can I have something that depends, how can I have a spin-orbit interaction that depends on the momentum of the motion between atoms and not on the angular momentum inside the atom? So it made sense? The answer is basically there are stray electric fields between atoms, and when the electrons move through those electric fields, there's a relativistic correction to the magnetic field that the spin sees. And it's actually very useful to think about atomic structures in terms of where is the electric field that gives rise to that spin-orbit coupling. Other questions? So I was prefacing the idea that instead of having this spin-orbit interaction, we should think about functions of momentum that are periodic, cosine and sine. And because momentum is periodic and spin can be periodic, the spin can actually wrap around the 0th direction around. So what do I want to say? If you think of momentum as periodic, you can think about the ring of momentum. And you can think about spin wrapping around the ring of momentum, either pointing along the ring or outside of the ring. And that starts looking again like this configuration of the velocity around the eye of a storm. How can you achieve such a phase? Now I'm in the realm of just writing Hamiltonians, and you'll believe me that there's some material that maybe realizes them. So I'll write this Hamiltonian up there. I'll give up on the proper periodicity of momentum, but it should be periodic with h bar pi over a. Multiplying it, sorry, h bar a over h bar pi. Yes, I think. There we go. You see why I'm leaving the period out. It's so much easier to talk about cosine p sine p. Right, so let's think about another type of a spin orbit coupled Hamiltonian, which we need to engineer. It doesn't come up naturally. With Sx, spin in the x direction, multiplying cosine p, and Sy multiplying sine p. Right, so cosine p is like projection on the x, sine p is like projection on the y. In every p, if you think about p as an angle around the sphere, this is like saying that Sx and Sy want to point in the p direction, right? But on the ring, right? To the angle that p represents, just like as here. And here I made this attempt of laying down the spin of the table, its xy components, and seeing which direction it wants to point as a function of momentum. Zero momentum pointing to the right. So zero momentum, this is zero, you want to be up Sx, and so on and so forth. Physically speaking, I want to illustrate this a little bit. If you take electrons with this momentum, then as they move slowly to the right, their spin is pointing, right, along the x direction mostly. But then as we probe more and more momentum states, we see that the motion is pinned to the spin direction. And as we wrap around the bend structure, so as we finish here, we increase momentum, we actually end up here, right? The motion starts going to the left instead of to the right because the derivative is negative. And the spin wraps around, starting pointing to the right, ending pointing to the right. That's a topological phase. Now, what is it good for except for making PowerPoint animations and talking about spin-orbit coupling? So this particular spin-orbit phase was actually suggested by no other than Alexei Kitaev, but in the superconducting context, where the S operators, for the expert amongst you, actually being the particle Hall degrees of freedom, the Nambu space. And that every topological phase is marked by edge states. That's one of the main signatures. In this case, the edge states in the superconducting spin-orbit coupled model, the edge states are actually Majorana fermions. So Alexei came up with this model 20-some years ago saying, yeah, I talked about topological quantum computing. Everybody's telling me, but there are no topological quantum excitations. And he went back and thought of a model that would give you such excitations. And then later on came proposals on how to realize this in p-wave superconductors in one dimension, how to get p-wave superconductors in one dimension that will give those Majorana fermions. This could give Majorana fermion and topologically protected quantum memory. And then if you have networks of these topologically protected braiding. So far 1D. Questions? So that's up to 2D. So in 2D, we need to think again about wrapping of spin, but now we don't have a ring, we have a plane, we have a torus that we need to think about. So here's my suggestion on how to think about it. So over here, I wrote a Hamiltonian that has the form of a magnetic field as a function of momentum, dot with the Pauli matrices. That describes the Hamiltonian of a two-dimensional system. This is the Bernoulli-Hughes-Zhang Hamiltonian for a churn band in 2D. Px, Py, every Px and Py has a direction the spin wants to point in. Starting with P equals 0, we see Px sigma x, Py sigma y, just like before. the spin wants to point actually along the z direction because there's a 1 sigma z here. That would be where the spin would point. Let me mark where the spin is pointing on the Bloch sphere, on the unit sphere. And now start exploring bigger and bigger rings of momentum. As I increase momentum a little bit, this one gets chipped away with this p squared, and we have px and py kicking in, giving you a directionality around the North Pole. And then as momentum increases further, this trend continues. And then it continues further to the degree that the 1 and the p squared flip, and you get a negative sigma z contribution. And at that point, the spin starts covering parts of the southern hemisphere of the Bloch sphere. If this continues to infinite momentum, we'll have a full wrapping of the Bloch sphere. That's the marker of topology in 2D. And that's what we call a churn band. There's a full wrapping. This is a churn band. This is an anomalous Hall insulator. If you put in an electric field in the x direction, you'll get a current in the y direction, even though there's no magnetic field. And I'll show you this. I'll show you how to understand this in a second. Questions on this setup? Yeah. Yeah, I love this question. Maybe I'll repeat it. So I was talking about the periodic structure of momentum, but here I came back to a continuum structure for momentum. So where did the periodicity go? Is there a way of doing this in a periodic model? Is that okay? Here. Disclaimer, we really need the lattice potential to do this properly. So we turn every px into sine px, we turn every py into sine py, and the p squared, we put the cosine on it. And then there's an art to determining whether this model is topological or not based on looking at what this h is at trims, time reversal invariant momenta, which are 0, 0, pi, pi, 0, pi, pi, 0. And that goes back to Charlie Kane and Shusheng Zheng, who thought this through. And that's a different conversation. It's very interesting to have. Like, how do you determine that the model is topological or not? But this is one way of determining it. Then you can see that a model like that could be tuned to wrap around the sphere. So that's a very good question. Thank you. And it answers it, right? Okay. I mentioned the anomalous Hall effect. I said this is like moving through a magnetic field. Let's talk about motion with a magnetic field. So motion with a B field, the dt is B cross V. V cross B, but electron is negative. So I think the sign is okay. But now we have another kind of object in the Hamiltonian, which is Berry curvature. I need to think about motion with Berry curvature. The Berry curvature is the curvature of where the spin points. Now, the spin is not pointing in one direction, it's pointing around the sphere. As you translate that to wave function properties, this is like having curvature instead of a flat space. I'm not going to prove it, but I'm just going to tell you how we handle it. So just like the magnetic field producing a force when it crosses with the velocity, the Berry curvature, we write as big omega, is like a magnetic field, but for momentum space. So the Berry curvature cross the force, dp/dt, the velocity in momentum space, gives you an anomalous velocity. So the velocity of a particle in a churn band has two pieces. One is the group velocity, the gradient of energy with momentum, plus the Berry curvature across the force that's applied. What is this Berry curvature? So just like a magnetic field is curl of a vector potential, a Berry curvature is curl of a Berry connection. And the Berry connection, you see, you take the wave function, you differentiate it with respect to momentum, project on the wave function. That's the Berry connection. If there's no spin dependence on the momentum, this thing is constant. Actually, if there's no spin dependence on the momentum, this thing is zero because there's no grad P. But because the spin depends on momentum, you can define this gradient object, and it behaves exactly like a magnetic field, exactly like a vector potential. Curl of it is a magnetic field. That's Berry curvature. Okay, and here's a bit of an attempt to simulate it, but in the form of a non-simulated animation of PowerPoint. So here's a map of Berry curvature of the band structure that I showed you before. So this is strong Berry curvature and no Berry curvature. And now we're going to see what happens when we apply a force on the particle in the x direction. This is real space. The particle will want to move to the right, but then it will accelerate, but then it will decelerate because of the finite band structure. As momentum increases, at first we go to the right, then we stop, then we go back, and then we stop, and then we go to the right, just like the spin that I showed you before. Moving fast to the right, then slowly to the left, then fast to the left. Those are called Bloch oscillations. That would happen in the x direction. But in the y direction, every time that the particle will go through a region with large Berry connection, with large Berry curvature, there will be this anomalous effect kicking in. The PDT is in the x direction, the Berry curvature is out of the plane in the z direction, and we'll get a motion in the y. This is what it looks like. So again, going through, there's a motion in the x that integrates to 0, but in the y, we just accumulate and go up. That's the anomalous Hall effect. If you have a band full of these electrons, they just all move up, and that's sigma xy. That's a Hall conductance. Make sense? This is an animation. It is not a simulation. But I'm still very proud of it. And another statement I want to give here as somebody who's currently teaching Introduction to Condensed Matter, the reason why we have Bloch oscillations is because look at this force. If the particle will continue moving to the right, that means that it'll absorb energy from the force, right? It'll absorb work. But if the particle is confined to one band, there's a limit to how much kinetic energy the particle can take. Therefore, it cannot, within the same band, continue moving to the right, because that would violate energy conservation. And that's why Bloch oscillation occurs. It's a way of, it's the only way that a single band can obey energy conservation. And this will be important in a few slides, as well as for the rest of your life, you know. All right, questions? This is the story of 2D topological insulator, and Andre Benevik, Taylor Hughes, and Shusheng Zhang realized early on that yes, you can make these models. This is, I think, after Charlie Kane and Jean Melek came up with a similar idea for graphene, and Duncan Haldane earlier for honeycomb lattices. So there is a lot of history here. But they were the first to realize that you can actually get those models in specific systems. You can make the spin-orbit coupling appear in specific systems, particularly mercury telluride sandwiched between two cadmium telluride wells. Those are semiconductors. They're just with heavy atoms, so there's a lot of spin-orbit coupling. Lawrence Molenkamp made the experiment. And what they showed is that if the thickness of the mercury telluride in between is in excess of 6 nanometers, this turns from being a boring semiconductor insulator into a topological insulator, which is still a boring semiconductor insulator in the bulk, but with edge states on the edge, wrapping around the system. And in fact, because of the spin-orbit coupling, there are two edge states, one with a spin up going one way, and another with a spin down going the other way, which has the freeway representation like this. You know, in Los Angeles, you can only understand things if you see them laid down on the freeway. But this is an empty freeway, so that will never happen in Los Angeles. And back when this was starting 18 years ago, or I don't know, 16 years ago, 15 years ago, there was a lot of excitement because all the wonderful things that could happen with topological insulators, spintronic devices, maybe dissipationless leads, Majorana fermions, quantum computing, the sky was the limit. It's been slow, I think, finding applications for these materials. But you know, they're a resource, and I believe that there should be a slew of devices that are based on topological physics that should come out. We just need to identify where they're based, or where they would be based, best deployed. Those were the simple ideas, but I think there are more subtle ideas that will come up if you consider particular systems and the needs of experimental groups in amplification, rectification, and so forth. So that's just an aside, something I believe in and I've started looking at. Okay, so far the introduction. Any questions? All right, so topology in light. So about 10 years ago, I realized, well, there's going to be a lot of interesting things if we take those topological ideas and apply them to driven systems. And the first idea was, topological behavior seems like a resource. Materials become interesting when they become topological. Can we make a semiconductor become topological just by turning on the light on it? That was the first thing we thought about. That was called Floquet topological insulator. I'll show you how it's done. Can we make topological photonic states? The topology that I showed you was for electrons based on their spin. Photons don't really have spin and they're bosons. Can we make them topological like this? You could, I won't talk about this, but if you're interested, you should know you could make topological materials detect infrared, deep, far infrared radiation, which is very hard to detect otherwise. You need to use cold temperatures and very specific materials. But topological materials, because of the spin orbit coupling and edge states, could be very good infrared detectors. And when you take topology and just apply it to the way you think of light, you can come up with new paradigms for controlling photons, new paradigms for amplification that are not based on 3-wave, 4-wave mixing. That would be where I hope to end. So whenever you turn on the light in condensed matter, I think you make things more exciting and better. So that's my motivation. Okay, so I gave a lot of introduction. So let's go to specifics. So the first thing I promised you, Floquet topological insulators, photo-induced topology. How do you do that? Let's take a semiconductor that has a little bit of spin orbit coupling. Every material has spin orbit coupling, but a little bit. So the spin orbit coupling is not strong enough to make a wrapping of the momentum torus over the Bloch sphere. But let's shine light. Let's shine light that makes a resonance between a ring in the valence band and a ring in the conduction band. Now let's do the standard trick in the book. Let's go to a rotating frame for one band and another rotating frame from the other, such that we take away the time dependence of this matrix element. In PowerPoint, it's really easy to do. Yeah, there we go. Now, instead of a driven system, we have a system with degeneracy. The Hamiltonian will resolve this degeneracy to make a volcano-like structure. But now check out the volcano-like structure, take a cut of it from the perspective of the spin. In the valence band, far away from the center, the spin is still pointing up over here. Now it used to point up in the center, but that's here. That's in the conduction band now. In the valence band, the center of the valence band had the spin pointing down. So wait, so here, at least in one cut, we have the spin wrapping around the ring. If you also have wrapping around this ring, which is here, then you win. And you have the wrapping of the Bloch sphere and a topological phase. So geometrically, it's easy to understand. It took us a while to come up with this picture. This was done with Victor Galitsky and Nate Lindner. But for the experts amongst you, for those who are curious, let me just look under the hood a little bit. So we have a Hamiltonian that's basically magnetic field as a function of momentum dot Pauli matrices, taus. Tau z will determine whether we're in the conduction band or the valence band, tau z up conduction, tau z down valence. And then we're producing a matrix element that mixes the valence and conduction, mixes the valence and conduction. You can do it by looking at tau x, you can do it by looking at tau y. So this G is a complex number. What is G? It's the matrix element between valence and conduction with the light, right? And the question is, what is G on the resonance ring? If G, which is a complex number, explored on the resonance ring, rotates around the origin of the complex plane, we win. Why? In terms of energy, when going from here to here, this term goes from positive to negative. And we just need this term to wrap around the origin of the complex plane, which would be exactly the same as wrapping the spin around the origin of the XY plane. So this would be full wrapping in tau space. Here's the numerics. We just took a lattice, periodic boundary condition in one direction, open boundary conditions in the other. We shined light in this form, and voila. Here's the new spectrum. How do I know it's topological? Because of this. Those are edge states. Those are the edge states I was telling you before about. And you see them in the numerics propagating along the open sides of the system. This was done in experiment. So in experiment, at first Nugetic shined light on the surface of a topological 3D insulator and produced copies of the spectrum on the surface. I don't want to dwell on it because it requires some more background, but I'll just point it out. But more directly, Andrea Cavallari's group very recently took graphene and irradiated it and showed that indeed a gap opens that becomes topological. This is, there are two ways of getting topological, Floquet topological insulator. I described one of them. It's linear in the amplitude of the drive. This effect shown here is quadratic in the amplitude of the drive. That mechanism was pointed out also by Oka and Aoshi about the same time that we were thinking about semiconductors. Sorry, Oka and Aoki. I mispronounced the name. Right. So this in this measurement, Andrea Cavallari opened the gap. He actually showed both modalities of Floquet topological insulator and measured sigma xy during the time the pulse was hitting the sample and showed the whole anomalous Hall conductivity emerging. So we were very happy to see this experiment, obviously. You know, after years of having to say, yeah, you can irradiate this material, people were asking, doesn't it heat up? Then that was the experiment where we can see it. All right, so questions? Yeah. Yeah, so the question is whether we irradiate the entire sample. If you irradiate only part of the sample, then you may get edge states. It might be interesting. You get edge states at the edge of the radiation spot, in principle. Yeah, you can do that. Yeah. Yeah, you can do that. You can even make phase defects in the laser, like angular momentum beams, and see localized spots showing up in the center of the beam. So it's things that Daniel Podolsky was exploring, and also in photonic systems, photonic crystal systems, Michael Rechtsman was looking at that. Very good question. All right, so I see I'm kind of running out of time, right? So we have until 10 minutes or so. So I wanted to talk about topolaritons, topological polaritons, but I'll skip that. So ask me later if you want, but the idea was that you can make combinations of light and particle Hall excitations that are themselves topological. Those would be topological polaritons, which I like calling topolaritons, but nobody else likes calling them that, so I'll just leave it there. And these are just really a superposition of excitons and light in a cavity. But I'll skip that because I'm really excited to talk about the recent developments on amplification, topological amplification. Oh, and very importantly, there was an experiment by Moti Segev that showed that the topolaritons are there. And yeah, I'm again very happy about this experiment too. Okay, I wanted to, so changing gears, using my 10 minutes very effectively. Let's think about, let me promise you something. I'm going to show you how you can get a two-dimensional topological insulator in a zero-dimensional system and use it to amplify light. So two things. So a periodic drive, it turns out, could be thought of as giving rise to extra dimensions. I love finding pictures to describe the principles I'm talking about. In this case, I really almost failed. And I said, yeah, I remember when I was a kid, there was this show, Time Tunnel, where they tried to tell, so this was the tunnel where you go in and then you end up somewhere in the 19th century, fixing things. I think in that show, low budget, the idea was a periodic structure in space gave you movement in time. Now, I want the opposite. I want a periodic structure in time that makes you think that you're moving in space. So it's like the dual version of the time tunnel. But I'm guessing most people here are too young to remember this. This is a more honest depiction of the show in black and white. Good Cold War kind of analog electronics kind of picture. This is the topic of synthetic dimensions. And like I was saying, this gives rise to new control paradigms, I believe. So let me walk you through it. Let's think about a periodic drive. Take a Hamiltonian for a spin half, have a piece that's constant, have a piece that oscillates with frequency 2 pi, with omega over 2 pi frequency. Think about the slow driving limit, omega much smaller than the Hamiltonian. I can take the wave function for the system. I don't want to diagonalize the system. I just want to look at its dynamics. I'll take the system. I'll expand the wave function in harmonics of the drive. No restrictions here. Psi n can be whatever it wants, but just attach different psi n's with different harmonics. I take that, stick it in time-dependent Schrodinger equation, and this is what I get. I get a hopping Hamiltonian. The psi dt depends on psi on the site, but it also has a hopping from n plus 1, n minus 1. What is n? The number of photons we took from the drive. Now it's like a tight binding model, except it's tilted because every time you take a photon from the drive, you need to pay energy. So here's what I mean. Periodic drive gives you an extra quantum dimension, extra spatial dimension. If omega is small, then this is fairly flat and you get a big chunk of the one-dimensional system. More dimensions. If you're a mathematician, immediately you should say no until proven otherwise, but I'm a physicist, so I say yes until proven otherwise. So more dimension, let's have double drive. Let's expand the wave function harmonics of the double drive. That corresponds to having a two-dimensional space, number of photons from source 1, number of photons from source 2. And it looks like a tight binding, and if you think about the system expanded in harmonics, it's like a tight binding model on N1 and N2 space, except that now there's a force in the direction of the vector omega 1, omega 2. It can be done. There's no problem with it, I think. Motion, because of conservation of energy, motion is restricted to this red strip. Again, Bloch oscillations. It's just a spin-half system. There's a limit to how much energy it can take in. So it cannot fall down the potential. However, it can move sideways. So far, so good? I promised two-dimensional topological phase and zero-dimensional systems. This is something that Ivar Martin and I started with Bert Halperin 5 years ago, and then Frederick Nathan joined in and made it even better. Here it is. Use a Bernoulli-Hughes-Chang band structure. Remember this? Sine px, sine py, cosine, cosine. Churn band from before. Every time you see a px, write omega 1t. Every time you see a py, write omega 2t. Same here. It looks the same. Physics, totally different. This describes a spin half that's irradiated by two cross beams, two elliptically polarized cross beams. Sine omega 1t and cosine omega 1t are the x and z components of one beam. Sine omega 2t, cosine omega 2t are the the y and z components of a different beam. In this case, the magnetic field of those beams. So elliptically polarized beams from two directions. But it is topological based on this. What the topology does, it takes energy from one beam and gives it to the other. Yeah. I'll talk about it. This is exactly the effect that I'm talking about. It's this amplification. This is what I meant by topological amplification. So let's see quickly how it works. So let's go back to that slide of an electron moving in a two-dimensional chain band. But now it's not an electron. It's the state of the system, right? So we have a spin half expanded in harmonics. So in this space of harmonics, N1 and N2, you can still think of the momentum space associated with that, but the momentum is just the phase of the drive. The phase of the drive is omega 1t, omega 2t. So this problem that I'm describing is exactly the same as an electron sitting in the valence band of a churn band and being pulled in the direction omega, omega 1, omega 2. Again, this is kind of what the system does. Every time that the system goes through a region of phase space, of momentum space that has a high Berry curvature, in N1 and 2 space, we go up a bit, perpendicular to omega. So there's no loss of energy. But what does it mean? It means that drive 1, we're losing photons. Actually, I should say it differently. Drive 2, we're losing photons. Drive 1, we're getting photons. Just to correspond to this. Drive 1, we're gaining photons. Drive 2, we're losing photons. The work done by one beam is positive. The work done by the other beam is negative. How much? Omega 1 dN1 dt would be the work done by drive 1. But what is dN1 dt? Do I have it here? Yeah. d1 dt, dN1 dt is the magnetic field times the force in the other direction, the churn number times omega 2. So the work is universal, omega 1 times omega 2 times the churn number in the construction I made, over 2 pi. So that's topological frequency conversion. You can think about it as an amplifier. You have a source that you want to amplify, you have a pump, the pump loses energy, the source gains it. Questions? So that would be a signature. This was measured, kind of. So it was measured on the IBM quantum computer. Somebody decided to program this on the IBM quantum computer and actually measure the energy going across. Otherwise, I think there are experiments about this kind of systems in BU as well that look at similar quantities. It's just hard to look at this work. All right. Okay with this? Can we realize this in not single spins? Okay, so here's the inspirational part of the talk. There is a system that has a Hamiltonian that's kind of like that, sigma dot A. It's called a Weil semi-metal. Weil semi-metal, we have sigma, the Pauli matrices, dotted with momentum. If you shine light, the momentum gets modified by the integral of the electric field, namely the vector potential, P minus EA. If you choose A to have this kind of symmetry, now it's the electric field that appears here, multiplying the sigma. And that would be a way to realize this topological energy conversion in a Weil semi-metal. And this was work that was done by Frederick over the last 2 years. How would it go? You would have a double-driven Weil semi-metal, so so sigma dot A. A would be the vector potential of 2 beams. Here's the dispersion, so a 2-dimensional cut through the dispersion of a 3-dimensional Weil semi-metal. You see there's a Weil node. I need it tilted. Why do I need it tilted? Weil semi-metals, they have a lot of electrons. Electrons are like ants. They all want to go in different directions. You need to give them a direction. Otherwise, there will be some amplification from drive 1 to drive 2 and some other amplification from drive 2 to drive 1. It will end up being 0. But if you tilt, you give them a direction. Here's a whole Fermi surface. Now, when you apply this light, each electron starts moving in momentum space in a motion that looks like a bagel. It's like a Klein bagel. It's a bagel that's inverted. on itself in half of it. If you have a sesame bagel, on half of the bagel, the sesame is on that side, but then it changes and the sesame is on the inside, in the other half. That's this shape. And now when we think about how topology emerges in the vial semi-metal, it goes like this. You have p-dependent pumping. Depends on whether the electron started out such that its trajectory contains the vial node on the sesame inside part, or doesn't contain the vial node at all. It will not pump in one direction, pump in the other direction. And our job is to overcome heating and make sure there's a net pumping. And this can be done, it turns out. So if you have frequencies that are harmonics of each other, you can avoid a big chunk of the heating. I love French names. We had Floquet topological insulator. This would be the Lissajous limit of this drive. And if you take realistic parameters for vial semi-metal, and you ask what is the relaxation time that is necessary to get pumping, to get positive amplification, if we get a material with a relaxation time that's in excess of 300 picoseconds, we'll have a really, really good amplifier for the terahertz regime. How much? How good? Check it out. Once you become positive, it's kilowatts per millimeter cubed. It's a really strong amplification if you can reach the right limit. So that's where things stand. Realistic materials are an order of magnitude away from this. But this is an example of how material paradigms can be actually deployed to take advantage of topological properties for actual devices, which is, I think, something that will happen a lot in the next decade. All right, so that's a good time to stop. I managed to cover topological Floquet insulators, skipped, and topological frequency conversion. But I'll still put it there as an advertisement. Topological polaritons, infrared, far infrared measurements using topological materials like vial semi-metals. All right, thank you very much.